Before we go and graph this and see what's happening here, what do we expect? Well, first of all, we see that we have damping, right? So damping is likely going to cause that spring mass system to settle down. For faster or for slower, we don't know yet, because we don't quite understand the magnitude of these numbers. But if we go ahead and graph this, we should see that this spring mass system is going to come to rest. Does the function support that? Well, there's no sines, there's no cosines in our equation, so there's not going to be any oscillation going on here, or any significant oscillation. So these are both decaying exponential functions. And so we can see here that as t approaches infinity, y approaches, well, what happens to this term? Well, as t approaches infinity, this is going to decay to 0. This is going to decay to 0. So that means y is going to decay down to 0. And sometimes whenever you do these limit analyses, just look at each of the terms and ask yourself what's happening to it as t gets bigger. And if the answer is it goes to 0, then your position is ultimately going to come to rest. Come to rest. So let's go ahead and plot this in Desmos. So here you see it. There's the initial position. Now our initial velocity was negative, and since initial velocity is negative, that means in our graph we expect a negative initial rate of change means the graph should go down. But also that means that the spring is being compressed initially. So it's at rest at the moment, but if we press play on our video, then that spring mass system is going to start going down. And again, what I'll do is I'll just insert a slider here, and we'll just look at this over the first 8 seconds or so. And then here I'll just make sure it does it just once, and I'm going to slow it down a bit. And now I'm going to look at the point 0, f of t. And I'll also just look at the point t, f of t. All right, so before we look at the actual observance of how the mass moves, let's just follow this point. So there's a little bit of a compression and back to rest. Now let's go ahead and add in sort of this green point, which we'll think about as the mass itself. It starts off at rest, and watch what happens over time. So the mass compresses a little bit and then returns to rest. So there's no oscillation in that spring whatsoever. And if we go ahead and plot both of the points, and we can see there's that point coming back to rest, a very non-entertaining spring mass system, and maybe not something you'd want in your car as a suspension system, because going over that speed bump would feel very odd, to say the least. So backtracking here for just a moment, the reason we had to choose this new method, and you can see kind of why this method has undetermined coefficients. It was the value of r, that coefficient that we did not know, and we were able to successfully solve for that. Now the reason we had to guess e to the rt is the base function, which, by the way, exponentials and sinusoidals are going to be the most common functions we run across. So if all else fails, those are often the turn two guesses: sine, cosine, exponential. So the reason we had to guess exponential in this case was, once again, because we had to find a function that, when added to its first derivative and its second derivative with these coefficients, they canceled out and gave us 0. Sine wouldn't work because now having to have the first derivative in this equation, whereas remember without damping this whole term was 0, we introduce a cosine amongst the sines, and those cannot add up and cancel to give us 0. So e to the rt, what we did is we said, all right, well, e to the rt, let's just find the right r that does this. So if y is e to the rt, its derivative is r e to the rt, second derivative r squared e to the rt, and then we substitute in for those components and we solve for r. One of the interesting things to note already is if you look at this equation here, which is often called the auxiliary equation. This is called the auxiliary equation because it's often just used to solve for something within the problem that's important. And this auxiliary equation, if you notice its coefficients are 1, 3, 2, well, those just happen to be the same coefficients in front of the first, or the second, the first, derivative and the original function, 1, 3, 2. So let's see if we can, before we take off with that pattern and just assume that that's all we have to do, is to solve r squared plus whatever coefficient is there, r plus whatever coefficient is there equals 0. And then once we had those two values of r that we solved, in this case this was factorable, then we constructed our two solutions because we have two values of r, so two different exponentials will work, one with negative 2t and one with negative 1t. By the superposition theorem, if you're dealing with a homogeneous differential equation, their sum is also a solution, and any constant multiple of the first function plus any constant multiple of the second function is a solution. And then we just used our position initial condition to form one of our equations. We had to take the derivative to get the velocity function, find the values of k1 and k2 that made both of those true, and we had our final solution that was then graphable. And I encourage you to think about limits like this. You don't have to get into calculus 1 type of limits, but oftentimes you can look at the function and just entertain the idea of what happens as t gets larger and larger.